your tutorial 3. And you see with all these problems, yeah, we have 3 problems here, and they are chosen because these give us different geometries in each case, right? In the first one, it's your Cartesian type geometry, XYZ. In the second one, this is cylindrical geometry, so RZ theta. And in the last one, it's spherical, so R theta 1, theta 2. So we gain a bit of experience in dealing with the different geometry types. And you'll see also that in the problems here, we are given the general framework, right? And if you are up to date with the videos, and I'm actually quite concerned about this class, whether or not you are up to date with the videos, but we had derived this general balance, which can apply in any, in fact, in any variable, in any type of balance, whether it's material, energy, momentum, or even electrical flux. So this general conservation of this general conservation equation covers all those types of balances, and also it covers all types of geometries. So these nablas here, those refer to the gradient. So this is the first derivative, second derivative in all dimensions of the geometry. So this is a very generalized balance, and uh, what we've been doing so far in all the problems we've talked about is look at specific forms of this generalized balance. You could look at it that way. So in tutorial 3, you are always given the generalized balance to begin with, and then the task is to convert the generalized balance into the context that's being described. So you read the problem, you figure out what type of problem it is, you figure out the geometry. Well, I've told you what the geometry is, but let's assume I didn't do that. So if you read the problem, then you figure out what variables are important, and then you go ahead and find the specific form of this equation. And once you do that, then you go ahead and propose boundary conditions, and then that's basically considered the problem is solved. Because then the next step is simply to go and apply numerical methods, and you can find specific solutions and so on. So tutorial 3 is all about taking this most abstract form, this very abstract balance that we proposed, and finding specific forms for it, and suggesting how this can be solved. So let's look at this first problem. So here we are told we have a 30 centimeter thick slab of concrete, and that has just been laid. So the reason for saying just been laid, obviously because we want to specify something about the initial conditions. And then the mixture has this mole fraction of water, XW. So the mole fraction of water in the slab, initially at least, is the same everywhere at XW. And then you see concrete takes a very long time to dry. In fact, it takes about 99 years to dry concrete. And in fact, a number like that tells you that it's a kind of equilibrium kind of drying out. So it never actually completely dries, but we consider 99 years to be, for all practical purposes, well enough dried. Well, obviously not for applications in the building industry, but that's another story. So anyway, yeah, we consider it dried when the fraction is below that. So we are given the diffusivity of water in concrete and through air, and we are interested in estimating how long it's going to take to dry that concrete given that geometry. And then we have some other relationships like the equilibrium between water and the concrete, and so on. Right, so the first step, formulate the balance. Well, in this case, it's actually telling you to formulate the general, well, it's saying formulate the governing material balance through the general form, right? And in fact, unfortunately, I didn't make a copy of that, but I'm just going to draw up a new one. So let's do it like this. Let's just write out the equation first. So ddt of alpha equals minus u nabla alpha, and then plus the diffusivity, and I'm going to call that the effective diffusivity of A, and then it's the second derivative, so it's going to be nabla squared of alpha, and then plus possibly some generation term. Right, so that's our generalized balance. Let's have these side by side maybe. So we want to develop the material balance for the slab problem. So we have the generalized balance to begin with. And now if you look at the problem, clearly we want to know the mole fraction as it's varying through the space. It's not saying there's any variation in temperature here. So we are assuming the temperature is the same everywhere through this. Obviously, if you are talking about a time span of 50 years, temperature is going to vary, but we'll take that as approximately constant. So let's assume it's in some climate area. It might even be climate controlled. This could be a slab inside of a building. So let's assume the temperature is constant. And then our velocity, we assume that if we are talking just about a slab, then we are not concerned about anything flowing around. So the slab is it's basically a stagnant fluid, and so we are not concerned about any momentum effects either. So we don't have to worry about momentum, and in fact velocity at all. There's no convection happening here. So the first thing we want to do, so the reason I'm saying all that, right, is to establish the first thing. What variable are we pursuing here? So the first thing to establish is we want to determine the variation of concentration of, and it's water, right? So water is the chemical that we are trying to determine the concentration variation of. So we want to know the variation of concentration of water in time and space. Right, we know it's drying slowly. So clearly time is an influence. And then it's talking about a thick slab of concrete. So I did draw that. Tried to do a nice little perspective drawing here. So here's your slab. So this blue part here, that's your slab of concrete. And we are interested in the way that the mole fraction is varying through that slab. Now we have to think about in which directions we are talking about anything varying, right? And if you look on the surface of the slab, right? So we assume now we have the slab that we've maybe dug a hole, and what we are actually looking at here is a hole in the ground, and we've poured concrete into that hole in the ground. So now, in what directions is might the concentration vary? And let's label our dimensions. So we can define x here, and then let's say this is y. So in the y direction, pointing into the page, and then of course you've got the z direction here. And you should always just check, am I respecting the right-hand rule? And yes, this approach does respect the right-hand rule. Okay, so that's our system of coordinates. And now let's think about in which directions things might be changing. So number one, out here, if you like, the slab is exposed on the surface up here, to the air, right? And we understand that water is diffusing from the slab up into the air. We assume that because we've said that this is poured into a hole in the ground, that there's no variation on the sides here, that water is not diffusing in this direction and it's not diffusing in this direction. So if you look at our dimensions, it's not varying in Z, it's not varying in Y, it's only varying in X, right? The concentration of water can only vary in the X direction. So if that's the case, our generalized balance can simplify quite nicely, right? So instead of saying nabla here, we can just replace that by ddx. So that's one thing. Now we know what space is. So we wrote quite a general statement here. We said we want to determine the variation of concentration in time and space. So space is three-dimensional, but now we've established that we only have to be concerned about one dimension, one of those dimensions. The other thing we've also said is that it's concentration we are pursuing. We said we are not worried about temperature variations. We are not worried about velocity variations. So alpha is C, the concentration. So we can write a more specific version of this equation, like so. So we can replace all the alphas by C's, so specific version of the equation. So we want to write all this in C, and let's just call it CA to specify A is water. And here we would, okay, let's just do it. So it's in the X direction. So ddx of, and that's of the concentration CA. A little bit awkward here. I forgot the dots. So this is ddx of CA. And then the diffusion part, so it's the diffusivity of A, and then nabla squared in Cartesian coordinates, it's d2 dx squared, d2 dy squared, d2 dz squared. So d d2, and I'm just going to put here, d2 CA dx squared. And this G is a generation term. That means if there's a source of something. So in this case, it's a mass balance. So this G is a source of mass. And if you look at what's going on here, we don't have a source of mass here, right? In fact, we have a loss of water. So there's no source of mass here. And the loss of water, it's not that we need now to write in a negative something for G. We have already accounted for the loss of water here in the diffusion term. So we don't have, there's no source of water here. If A is water, there's no source of water. So we know G is going to be 0. And then also U, clearly nothing is flowing here. So there's no bulk velocity to speak of. So U equals 0. So our equation then becomes quite simple. Right, it's only the diffusion equation that we have. Right, so we can neglect this term. We can say that term is 0, and then we can neglect the generation term as well. Right, so that's the specific form of the equation when we start out with this generalized version of it. Now we are going to rederive this from scratch, right, without using the specific form of the equation. So that's where I say this session is also in a way a revision for the test, because of course that's one of the topics for the test. So let's go back and look at what the problem asked us to do. So formulate the governing material balance through the general form, right? So we've done that. Here's our specific form when given the general governing balance. So we have done this first part. We've formulated the governing material balance. And now formulate the governing material balance from first principles. So when you see that statement, that means do it without using the generalized balance first, right? Now, when you tackle these problems, right, whenever you are developing your material balance from first principles, you always start with a sketch, right? And in fact, we already talked about it. So we have the sketch, and we have defined our coordinate system. And I'm just going to move this here. In fact, it's fine. Let's let x be 0 here. So x is 0 at this position. So that's 0 there. And then let's let the thickness here be L. So let the thickness of the slab be L. And we are interested in the diffusion of water out of this slab. So we are interested in diffusion that's happening here. So diffusion is happening all the way through the slab to the surface. And you can see these red lines here. So that's where I've already drawn in the control volume. So we are choosing a control volume at position X, and at position X plus delta X. Okay, and let's call this area A. So this area, how do I draw this properly? Okay, let's just try and shade this area. So talking about this area here, I'm going to call that area just simply A. So that area out there, let's just make that not so overpowering. So that's the area A, and that's the area that's normal to our flux. So always get all your definitions in. So that's area A. We can see now what our control volume is, A and A plus, X and X plus delta X. And so if we write our balance, we can imagine there are only two influences on this control volume. We have diffusion into this control volume, and we have diffusion out of this control volume. Right, so those are the two influences that we have to count. So when deriving the balance from scratch, number one, you create the picture, you make clear which direction you are defining the changes to be happening in, and you define all the quantities. So far, looks like X and X plus delta X, area A, and we can see fluxes here. So let's write the balances. So in fact, before writing the balances, let's write about the volume. So we are interested in the control volume. So control volume equals, and we can say delta V equals, and it's going to be A times delta X. And then in that space, so in the control volume, number of moles is, and we can write here delta in A equals concentration of A at position X times the delta V. Okay, and there, of course, the concentration is generally varying in all directions. So it's varying in, or we can define it to vary in Y and Z, just that it's a trivial variation. The gradients are all 0 in those directions. So you could add other terms here u dc dy and d2ca dy squared, and do the same for z, but those gradients will all be zeros. So so that's the reason why we only retain these terms. We know these gradients are non-zero in the x direction only. Right, so we've defined the number of moles and the sub-volume. Now let's define the fluxes. So we can say here, entering the volume, flux, the flux there is NA, and that's at position X. That's going to be minus D sub AE, and then it's dCA dx. And here we have to specify that this is at the X position, because the gradient is generally varying as you look up here. So when you look up through this through the slab, you've got some profile. So if you were to sketch it, there might be a concentration like this, right? Your concentration is varying like that. So if this is our graph, if this is CA here, if we are plotting CA as a function of X, then we expect we will have a high concentration of water near the as far away from the surface as we can, and then as we get closer to the surface where water is actually diffusing away from the slab, then we'll have a lower concentration. Well, that's what we expect to happen over some time. It might not be true initially, but the point is the concentration is varying like this with X, and that means our gradient is varying also. So we have to be specific here that that's at the X position. So entering the volume, that's the flux. So no, that B is there. And then leaving the volume, the flux is going to be the flux at X plus delta X, X plus delta X. And then it's going to be the same form. It's the same process. It's also diffusion at that point. So it's simply going to be the same type of flux, just at that position. So delta X there. Okay, and in fact, that's it. Those are all the influences to this fairly simple problem. So let's stick it all together. We can say then that the overall balance is then given by, so the rate of change of the number of moles there. So ddt of delta in A, the rate of change of the moles in that subvolume, equals the entering flux. So it's going to be NA at position X multiplied with the area that's normal to that flux. So if you look on the picture again, you've got the flux pointing up in this direction. That's our X direction. And then the area that's normal to that flux is this green shaded area that we did here. So that's the area. So we can simply write this as A. Yeah, so that's the area A. So that's what's coming into our subvolume, and then leaving the subvolume is the flux at X plus delta X, X plus delta X. Right, so that's the overall balance, and then and the kind of generalized version of that. So let's write the specific form of this by substituting what we just wrote above. So for delta in A, we've got CA at X times delta V. That's CA delta V. And then for delta V, we have A delta X. Right, so this delta V, of course, is not changing with time. That's our choice of subvolume. So we'll take this out as a constant of this differentiation. And then for delta V, we can substitute A delta X. Right, and then for NA at X, we've got this term, so the diffusivity. So the flux of A is only due to diffusion, and then we also have diffusion only for the flux that's leaving, so this term. So make that substitution here. And then you can notice here that a minus minus that we can rewrite as a plus. And so we can just move this term out in front. And then we've got minus the other term here. Minus this term. Okay, so that's the equation we have so far. Now, looking at this balance, in fact, let's just copy it from this point. Looking at this balance, you can see that the area appears in all terms. So area can cancel. And then you've got delta x here. You don't have delta x here, but anyway, let's divide through by that delta x also. So we get rid of area first. And then let's divide through by delta x as well. Okay, so delta x is divided out. Then, of course, we could extract this diffusivity as a constant here. So let's also take this out as a common factor. And now, if you look at this equation, the next thing we would want to do is take the limit for delta x going to 0. So we take limit delta x going to 0. So you can see then that that's simply going to give us the second derivative here. So it's going to be dCA dt, dC dt is equal to d2CA dx squared. d2CA dx squared. Okay, so that's what we got when we took the long route and we derived the equation from scratch. And if you look at what we did up here, we got the same balance, right? So if you take the generalized equation and you just apply modifications, you just look at your context and say, okay, what geometry do I use? What type of balance is it? Which terms can I knock off? And then you arrive at the equation there. And now we can see if we do it rigorously and from scratch, we get the same result. Okay, any questions or comments there? Okay, so that's the first part of this. The second part is then to establish the boundary conditions to solve this problem. And so let's think about what's going on here first. Number one, we know that initially through the slab, we had the same concentration everywhere of water, right? When the slab was just poured, of course, the concrete had been mixed. And so it had, we assumed that the concentration of water was the same everywhere throughout that slab. So we assume initially, at least, that that the concentration was the same. So we can state that here like so. We can say Ca initially. So we say that as t equals 0, and then we can say for any x position. And in fact, you can also say in y and z also if you want. So I'm just going to write it like that, and then that's equal to the initial concentration. So the initial condition is that the slab was the same everywhere. So that's one condition that takes care of the time part of this. Now, if you look at this equation, it's first order in time and second order in x. And you count that up then as 1 plus 2. So that's going to be 3 boundary conditions that we need to solve this problem. So the other boundary condition we can look at is at the surface here. Clearly, we have diffusion away from this slab. And let's draw first what we think is happening there. So at the surface now, so in here, we are just inside the slab. So this is the slab side of it. Slab, right? Slab. So we're looking in the slab here. And then out here, we have the air. Come on. Okay, so out here, we have the air. And so our diffusion, of course, is from the slab into the air. So we've got diffusion through the material of the slab. Oops, what's going on? Okay, anyway, time on. Let's just do this. So you've got your diffusion from the slab into the air. And we can identify a couple of things. Number one, in the air, there's a certain bulk concentration of water. So we can identify Ca bulk. And then near the slab, so let's just define that at some arbitrary position that's far enough away from the slab that we can see the bulk in the air there. So let's say Ca bulk in the gas here. And then near to the slab, we have actually a higher concentration of water. So we have a certain amount of water in the air, just due to other influences. And then due to the slab here, near the slab, there's going to be a higher concentration of water. So we can think about Ca at this position. And then, of course, there's another concentration just inside here. And so if we were to sketch all that, let's do it in this direction. We have, on the gas side, we have a certain concentration of water. And then near the slab, we have a certain other concentration. We have a higher concentration near the slab because that's a source of water, right? So we can imagine there's going to be some continuous variation in the air above the slab. So this is the air side. And this is the slab side. Now, on the slab side, we have some concentration of water initially in there. So there's a high concentration. But then near the slab, there's going to be, near the interface, there's going to be some of that water will have started leaving the slab for the air. So some of the water will have left like that. And so it will reach some value here. And so let's let the value here be this one. And then the value here be this one. Right, so in each case, there's a bulk concentration of water in that phase. So in the slab, there's a bulk concentration. In the air, there's another bulk. And then there's some change that's going to happen. So at the interface between the slab and the air, there's a discontinuity in the concentration values. So on the slab side, you have a certain concentration. And you see, this is the equilibrium value, right? So between any phases, because there are differences in the environment, right? In the air, we pack water differently to the way we pack water in the slab. In the slab, you can imagine finding liquid water. In the air, clearly, the water is a vapor. So there's going to be a discontinuous jump in the concentrations here. But there is an equilibrium between these two values. So if you think of your thermodynamics course, there is always an equilibrium in the concentration value across phases. So that's that equilibrium shift there. And then there's another shift, which is the difference between the equilibrium value and the concentration in the phase, in the bulk of the phase. So of course, when the construction workers mixed the slab, mixed the concrete, they didn't go to the thermodynamics tables and look up the equilibrium value of water in air. There's no reason to do that, and that's not well, generally speaking, we don't think they went and did that, right? So generally speaking, there's a different concentration here, and so there's going to be some transition zone where we get to the equilibrium value. Um, and here you can think of this as a fixed value, right? In the air, there's a certain amount of water, and of course, climate change is changing all that, but we can accept that in the atmosphere, there's a certain amount of water, and we consider that fixed. And then the equilibrium value of that water is not the same as the value as the concentration of water in the air. That's a function more of the weather patterns and the amount of sunshine that's causing a certain rate of evaporation and all that. So there's a lot behind the value of water, the concentration of water in air. So there's a certain amount there, and that's different generally to the equilibrium value, and that's the equilibrium between these two phases. So we have to label all these differently. So we can identify in the gas, there's a certain bulk value of A. So there's bulk in the gas here, and there's a bulk amount in the slab here. So Ca bulk in the slab. So we can define those values. And then we can also define the interface values, which are the equilibrium values. So, and I'm going to do that here. So so all this discussion is over this boundary condition, right? So at the air slab interface, where x equals L, right? Remember from our picture here, we defined L. We said x is 0 down here, and then the thickness of the slab is L. So that means we are talking about the x equals L position. So where x equals L, we have, and we're going to say here, the concentration of A in the slab. Well, we've been calling that Ca, right? So we've always been referring to the slab concentration so far, so we don't need to say slab here. So the concentration of A, and now we want to say just inside the slab. So we can say here, the concentration of A at x equals L, and I'm going to say L minus, L superscript minus. So that means for values of x just inside here, right? So we're talking about just at the interface, just inside the interface, then we know we are talking about the concentration in the slab. That concentration must equal, and it's this drawing. So that's that value that we are talking about now. And now we know there's an equilibrium relationship with the concentration in the gas here. So that concentration must be at the equilibrium relationship with the concentration of A, which is just in the gas. So now we have to specify the gas phase, A comma gas. And then that's going to be at the position where x equals L plus. So just above just above the slab surface, there's a certain concentration in the gas phase, so that's that value. And using the equilibrium constant, then we can get the concentration just inside the slab. Okay, so that's the boundary condition we can apply there. Any questions or comments on that? And by the way, of course, if your air is well enough mixed, so for example, if you have the slab exposed to a turbulent air stream or something like that, it's going to be well enough mixed that this is going to flatten out. And then you could just use the bulk. You could just look up from the table from your water table or something in air under those conditions, what's that concentration? So that would simplify it if the interface value was actually the bulk value of water in air. Okay, so that's the one boundary condition. And now we have two boundary conditions. We need the last boundary condition, which is down here. And then sometimes what we use is we say that, well, if this distance is great enough, if L is great enough, then we haven't made any changes down here. But of course, now we are talking about variations over 50 years. Over the course of 50 years, we can imagine that water from down here will have started to move. So the most I would care to say here is that the second derivative is 0. In other words, we can say that down here, your gradient should at least be flat. So if you were to draw the gradient, well, in fact, we drew it already. So let's say this is the gradient we reached. Then the most I would like to say here is that by this point, the gradient is equal to the gradient here equals the gradient there, right? The gradient here equals the gradient there. So dc dx at this x position is equal to dc dx at that position. So if that's the case, then we can just use this condition. We can say d2ca dx squared, and this is specifically at x equals 0, x equals 0 equals 0. Okay, so those are three boundary conditions, and that will be enough to solve the problem. Any questions or comments there? Okay, so that's problem number 1. Let's look at number 2 now. So problem 2 talks about the manufacture of O-rings for space travel. And in fact, that's something of a notorious reference. So I don't know whether you're up to date with your knowledge of space travel, and but the Challenger was a shuttle that exploded very soon after takeoff, and in the investigation, it was eventually discovered that it was the O-rings that were at fault. So the O-rings that were used in that shuttle's construction were not suited for the stresses that it was exposed to during that launch. And so in this question, it's a kind of throwback to that case. So I don't know whether the investigators did the kind of derivation that we are going to show now, but that's what that refers to. So O-rings and space travel, it has that kind of background now. So we are going to take the same approach, right? We are overall interested in the steady state concentration profile through the polymer layer. In fact, let's talk a bit more about the problem first. So O-rings, right? So we know what O-rings look like, but we are going to simplify the picture for O-rings. And I've drawn a kind of modified version of my cylinder problem here. So let's take an O-ring to be something like this. So you've got a cylindrical object where the Z dimension is short, and then you have a hole running through the center, right? So there's a hole through the disk and through this cylindrical object. So that's how we'll model an O-ring. And then, of course, we have to choose our control volume and so on. So in this O-ring, we are interested in the variation of concentration across the O-ring itself. So it's empty in the center, but through the O-ring, there exists some concentration profile, and we want to determine what that is, obviously. So let's read what the problem says about that. So it's a 5 centimeter, that should be thick, obviously, thick polymer layer is coated onto the exterior of a permeable 20 centimeter thin pipeline, through which component A flows. So this is actually talking about the manufacture of O-rings. So let's draw those dimensions. It's a 20 centimeter thin pipeline. So you've got a pipeline, and it's 20 centimeters. 20 centimeter, so I guess that's diameter. So that's 20 centimeters. And we are depositing 5 centimeters of polymer onto that. So here's our polymer layer. So it's a fairly thick layer, considering that inside is 20. So this is 5. And so this is all polymer. Oops. And upon achieving a minimum concentration of Ca star at all points in the polymer retains its sealing capacity at low temperatures without becoming brittle. So you see, it's a very clear reference to this O-rings in space travel problem. So yeah, I remember, I think I had watched a documentary on how they did that investigation. So that's how I came up with this problem. So we want C star, and let's see what the source of A is. So A in the pipeline is CAP and is 0 in air. So above the polymer layer, the gas concentration is CAG. So let's think about that. You've got component A in the pipeline. So let's, for component A, remember we've got polymer here. Now A is flowing through here, and the concentration there is CAP. CAP. And so it's flowing through here, right? If we look down at this picture, it's flowing into this inside this green circle here. So your A is flowing in here, and then it's clearly diffusing out from here. So it mentions things to imply the concentration of A is very low out here. So it looks to us like the concentration of A is going to vary like this. There's going to be the highest concentration here, and then it's going to drop as we reach the outer surface. And in fact, a useful thing to do also is to try and sketch out what we expect to happen over time. So let's redraw this. So we can imagine initially there's none of A. Let's say this was the 0 concentration value. And then after some time passes, some of A will have diffused into the polymer. So it might be like that. And then as time goes on, more of A will enter until we reach some saturation value here. And we don't need to go all the way till saturation. We just need to guarantee that we have at least A star, right? It says upon achieving a minimum concentration of A star in the polymer will retain its sealing capacity. So that's what we want. Now, if we look at what we've drawn here, we can see that the low point is going to be the point near the surface, right? We know there's diffusion out to the air here, so that's always going to be the low point. So we want to find out, when do we reach A star? So let's say, let's just call A star here. So we want to know, how long does it take before we reach A star at this point? Right, so that's how we can interpret this text and figure out what the question is. Okay, so the concentration is 0 there. So okay, so that's the problem read. That's all the information given to us. So the first question, what's the steady state concentration profile through the polymer layer? So we've sketched out some ideas for that here. And then formulate the governing balance through the general form. So again, we start out with our most general balance, and let's just copy that. And now clearly we are doing a material balance, so alpha is C. And then let's think about the directions in which this O-ring is varying. Right now, we haven't really talked about it, but the O-ring obviously is not an infinitely long thing, right? Well, we've been talking about the manufacture of O-rings. So presumably what's happening here is we have this pipeline, we have this polymer layer outside this pipeline, and then A is diffusing into this polymer layer. And we presume the next step will be for the manufacturer to take slices through that polymer, and then you form the O-ring. So remember, if you read this problem, you've got here manufacture of O-rings. So we are not modeling an actual O-ring. We are manufacturing. We are talking about modeling a long pipeline, which is a polymer layer. So what I'm trying to say then is that in the Z direction, we are not concerned that we have end effects, that we have significant end effects, right? If you had a short O-ring, let's say the O-ring only looked like this, right? If it had this appearance, then you can say, well, the area here is not that different to the area here, so we have to be concerned about variations in the Z direction and in the R direction. So that's not the case here. This pipeline is, we consider long in comparison with the R direction. So we're not worried about the change in the Z direction here. I mean, that's one contribution to saying we don't need to worry about the Z direction. Another thing that concerns us about the Z direction is, what if this concentration is varying in the Z direction? So the gas that's flowing inside the pipeline, what if that was being depleted? We know component A is diffusing from the gas into the polymer layer, and A gets depleted as you go further down the tube. If you look further down the tube, some of A diffuses here, then some of A diffuses here. So A keeps diffusing into that polymer layer. So are we not depleting component A as it's flowing down this tube? Well, if the concentration of A is high enough inside this tube, then and if your diffusion of A into the polymer layer is low enough, right? And it might be Ca star, the amount we require is actually a low concentration in comparison with the concentration in the fluid. If that's the case, then yes, we could say, I don't anticipate that this concentration is going to vary much in the axial direction. So if we assume that, then we can say that we expect that all gradients in the Z direction are going to be 0. Right? So that's one. And if we are talking about, right, clearly we are talking about cylindrical geometry now. We are talking about R, Z, and theta. So we know it's varying in the R direction. That's what we sketched out here first. We said the concentration is going to vary across the thickness of that O-ring. So we know that is going to feature. For Z, we've made a couple of arguments now that possibly we could get away with not using Z. And then in terms of theta, theta is the angle. So if you look at a point here, right, the angle, and you see there's no real reason to think that there's going to be a change in this direction, in an angular change. The question doesn't say anything about treating different angles differently. So we don't anticipate that we have to worry about the angle either. Right, so with those with those considerations, we can say only R concerns us. Now, when we go to this equation, we have to look up the form of this equation for this geometry. And in fact, in the notes, I've given, where is it? I pulled it up for this session. I think it's here. Yep. So the forms of nabla. So for Cartesian coordinates, it was simply ddx, ddy, ddz. For cylindrical coordinates, it's ddr plus 1 over r dd theta plus ddz. So in this case, we said dd theta and ddz are 0. So we can ignore those two terms. And so we've got just ddr. Then for the second derivative, so we can ignore d2 d theta squared and d2 dz squared. So those are zeroed out. But then we have this form here, right? So we can write this balance. We can say here, number one, this is written in terms of concentration. So our balance needs, this is a material balance we are doing. So we can write CA. This is CA. Now, if you look at interior points, there's no source of A. But anyway, we'll get to that. We'll look at the specific forms just now. Let's get rid of these nablas. So nabla itself, we just saw is just DDR. So we can just write this as DCADR. Right, so that's that part. And then D2 CA, or nabla squared CA, we have to write 1 over R DDR. So this is going to be 1 over R DDR of R dCdR. So R dCADR. Okay, so far so good. And then, like I started to say just now, there's no source of A that is inside of the space, right? Whenever we write balances like that, we are talking about inside the material. We are not talking about the boundaries. We know A comes in through a boundary. So you could say in the boundary, we will account for the source of A from the gas flowing in here. But in the material itself, right, this balance that we are writing describes the changes inside the material, inside the control volume. So inside the control volume, there's no source of A. So there's no, we don't need the source term here. We also notice that there's no flow of A in here either. There's no convective flow of A. So we can similarly neglect the convection term, leaving us just with this form. Okay, so you can see the pattern here. And you can, if you want, expand this derivative. So if you differentiate this, you can see both these are both these are functions of R. You've got R and dCdR. So you can expand this and write this as, so you can differentiate the R and leave the dCdR part. So you can say dCADR. Plus, and then you can leave the R and differentiate the dCdR. So you can get here R dot D2 CA dr squared. Right, so if you expand it out, you get that. Okay, Now let's derive this from scratch. And I'm not going to go into as much detail as I did in the previous case. So please ask me questions if you'd like to. Um, so number one, we can just write the number of moles in the space. So we can write the rate of change of moles in the space. In fact, let's just copy the framework a little bit. So we can specify our control volume, our amounts, and our diffusion flux. So all this, we just have to write the same version of these parts. So our control volume, let's think about that. Our control volume, we can see is between R and R plus delta R. So the area here can be approximated as 2 pi R, so the circumference of the inside, multiplied by delta R, so that's the area. And then we can choose also a distance here, delta Z. So we can say here our volume is 2 pi R delta R, and then we are taking some basis delta Z. So that's the volume. And then here, the number of moles in this control volume is going to be the concentration at that radial position R multiplied by that control volume. So that's there. And then we've got diffusion in. So here we've got diffusion in at this face and diffusion out here. So diffusion in here, that's at R, and that's at R plus delta R. So we can write this as the molar flux of A at position R, and then that's simply dCdR at the R position. And then the diffusion flux out of the volume is R plus delta R. And it's there, R plus delta R. And now there is a piece I would like to add here, which is about the areas. So in the earlier case with the slab, it was very easy. We had the same area right the way through. But if you think about our diffusion in this case, here we have diffusion in this direction, and you can see the area that you get here on the inside is not the same as the area here, because the radial position is different, right? If you look at this circumference and compare it with this one, circumference is larger, so the inside area is going to be larger as well. So we can say area, the function of R position, is going to be the circumference 2 pi R, and then the distance there is delta Z, and then the area at R plus delta R is going to be this one. So the area at R plus delta R is 2 pi times R plus delta R. Okay, so those are your areas now. And so given our overall balance, if we stick all the pieces together, it's going to look like this. So this delta R, so that's CA at R times delta V. And our delta V is our fixed choice, so that's a constant of differentiation. So we take out the delta V here, and we've said that delta V is the same as this thing. So we can substitute that here. And then our NA, and sorry, I should have said here at R instead of X. So that's NA at R. And this is going to be the area at R plus delta R. This is the area at R. Okay, so this is our flux at R. So the flux at R is this. And then the area at position R is this. And then the flux at R plus delta R is this. And then the area at R plus delta R is this. So far, so good. So that's our balance. And if you look at this balance, you've got common everywhere. You've got 2 pi and delta z. So you can see here 2 pi delta z. Here you've got 2 pi delta z. And here you've got 2 pi delta z. So that can all cancel. You have R here, but you have a different R here. This is R plus delta R. So anyway, let's just do that first cancellation. Let's do this the long way around. So 2 pi and the delta z can cancel. Okay, and now we would like to divide through by R delta R. So let's do that. And let's just do it as a new copy. I'm just thinking, okay, let's do something a bit different here now. What I want to do is claim that this is a function. So this a function, it's a very trivial, simple function R. So I can just bring this R inside of these brackets. I can say this is R at R, right? So that looks, what I've said, it sounds silly until we think about what happens here. So we could think of this as the function R just evaluated at R plus delta R. So we could say this is a function at a specific argument. So if we say here, this is dot R, and we are evaluating R at R plus delta R, then you see this is valid, right? So be careful of that, right? So once more, you've got R plus delta R on the outside, and then you've got next to that a function being evaluated at R plus delta R. So instead of retaining R plus delta R out here, we can just bring that inside of this function evaluated at R plus delta R and call it the function in its own variable, right? So that's a common trick that's used to help us derive these equations. And you can see the reason is that now we've got the same function in both these square brackets, right? So be sure you fully understand that method, and then you'll see we get the same function like that. Okay, and you can see here minus minus, so that's going to be a plus. So we are going to get nicely R plus delta R in the plus position, and then minus the function at R. And now we can also take our DAE as a constant. So I'm just going to put another bracket here and eliminate this DAE. And now I want to divide through by R delta R. Now, just be careful here. Avoid the right? Don't fall into the trap of dividing this R by this R, right? It looks nice that this R and this R have the same form. It looks like R can cancel everywhere. But you see, this R is not the same. This R is evaluated at R plus delta R. So it's not the same as this R here. So when we divide, we have to respect that. So this, in fact, I want to write this as over R. So let's divide by the R there, and then I want to divide this thing by the delta R. Okay. And now you can see clearly if you take the limit delta R going to 0, you're going to get a nice derivative here. And I'm just going to copy that limit. It's always a bit annoying to have to write this thing. So taking the limit for delta R going to 0, gives us, and let's just copy this, gives us DDR of this function. DDR of this thing. Right. And that's the result we were looking for, right? If you go back and look at what we did when we used the generalized balance, we said that straight away. We happened to go ahead and differentiate this out, right? If you go and differentiate this out, right? Totally unnecessary. I don't know why I went and did that, because now I've kind of messed up what I was trying to show there. But anyway, let's just do it. DDR, you can write this as D2CA dr squared, so you can differentiate the first one and leave the second one alone. Where is my cursor? So D2 dr, so that's the one, and then the other one is plus. You differentiate the R out, leaving you with just DCA dr. Right, so now if you compare the two, you can see you've got exactly the same solution. Right, so this approach is based on a rigorous from first principles approach. The other one we got just by applying what we know, by applying our generalized balance that applies to any geometry and any variable. And now we see we get the same result as when we do it from scratch. So I guess that's the point that we're trying to make in this tutorial, that we now have this fantastic power of this generalized balance, and we can use it to investigate any conservative variable, and we can use it in any geometry. Right? It doesn't matter whether it's slab geometry, Cartesian geometry, or cylindrical geometry, or even spherical geometry. And in fact, there are some other weird geometries you can also think about, like triangular geometries and so on, and it still works. So it doesn't matter your coordinate system. In this nice generalized equation with this nabla form, you are able to develop all these material balances. Any questions or comments there so far? So for the last problem, and of course, boundary conditions. So please read in the notes. We actually talk about this type of problem in some detail about the boundary conditions there. Okay, so let's look at the last problem here. So we are interested in the removal of sulfur dioxide from a gas stream. So there's a certain process and there's a gas stream exiting that process. And we want to clean up the gas before it's released to the environment. And we're doing that by passing this gas through a moving bed of permeable spherical particles. And so maybe a quick sketch here. So we've got some particles. That's exposed to some gas. So out in the bulk here, you've got your sulfur dioxide gas. And we are hoping to trap as much of the sulfur dioxide into our particle as possible. So we've got this gas diffusing inside of this particle. And in fact, it will keep diffusing as long as the concentration gradient encourages it to. So if near the center you have a low concentration, then everything will keep diffusing in towards that particle. Okay, so let's see, any other information? So sulfur dioxide in the gas stream. It's actually in a bed of permeable spherical particles. And we are actually modeling one particle. The problem doesn't actually say this, right? So normally I would specify quite a bit more so that it's clear what we want to model, because we could also model the bed of particles instead. But I know in this tutorial I wanted to do slab geometry, slab geometry, then cylindrical, and then spherical. So here, here's the sphere of interest, which is the particle, and then we are going to pick some radial position r. So we can define our control volume. So there's r here, and then r plus delta r is there. So this is at r, and this is at r plus delta r, r plus delta r. And then the same approach applies. In this case, is it also just diffusion? Yeah, it looks like it's just, we are just relying on the gas diffusing into the particle. Now, note, of course, that the actual diffusion is in towards the particle, but the real, the definition is always in the positive spatial direction. So R is defined 0 here and looking outward like that. So we define the flux to be in that direction, but of course the value of the flux might be negative. That means it's diffusing inwards. That's fine. So again, we could start with the generalized balance, and we could go and look up for that geometry what the nablas work out to be. So you could go over to your table of forms for the nablas. So now we have spherical coordinates, and we only anticipate variation in the r dimension, right? So the next step is think about all the dimensions. So we can see clearly in the r direction, right? There's a driving force, right? Your component is trying to diffuse in to where the concentration is lower. Now, in the angle direction, there's no variation. So let's see if we can draw this in 3D. So you've got, imagine sticking out. Okay, let's use the different. So imagine you've got sticking out of the page your one dimension here. So let's say that's r, and then let's imagine an angle here, theta 1. So that's there. And then let's imagine another angle, theta 2, which is on this plane in this direction, theta 2. So in fact, what this spans out is a little subvolume that will look like this. And drawing with the mouse is awkward. I can't draw this well, but yeah, it's pretty challenging even. Okay, so here, this would be the kind of subvolume, this weird little shape. But you see, we have no reason to believe that there are changes in the angular direction like this, right? This spherical particle is exposed equally at all angles to the same gas. It's not as if gas at this particular angle is different to the concentration of the gas on that side. So our two angles, we don't expect variations in. Our only concern is in the r direction. So if that's the case, then nabla is simply df dr, right? You've got your dd theta 1, dd theta 2, so we can ignore those. And then nabla squared f, only the first term survives. These other ones are zeros, right? So our balance, you can follow the same steps, and you can show that that for the r dimension, it's going to be 1 over r squared ddr, r squared dcadr. Okay, so you can do that step, and let's actually just do the first few steps here, because you can see by now what the pattern is. So let's just get these steps right. Okay, so for spherical coordinates, Your volume now, if you think about the volume of the space, the inside area of this sphere, of course, is 4 pi r squared. 4 pi r squared. So that's the area of a sphere. And then the thickness of the sphere is delta r, right? So I'm looking for the volume of this thickness, right? This is our control volume. You can imagine the skin of a ball. So if you take a ball which has a thickness, a certain thickness, in this case delta r, then you take the surface area of the ball, the inside surface area, and multiply it by the thickness. So delta r. So that's your volume. And then, of course, we know that's the number of moles, concentration times that volume. Then your flux, the same fluxes apply. So dCdr and dCdr, and you can specify at r and at r plus delta r. And then we are obviously talking about, we've got a certain flux here at r, so that's what's arriving. And then we've got a certain flux here leaving. So we've got an arriving flux we need to multiply by the area normal to that flux. And so that's obviously going to be 4 pi r squared, 4 pi r squared, no delta z this time. And then leaving, so we've got the form for the diffusion flux. We need to multiply that by the area at r plus delta r. And so this one is going to be 4 pi, and we can write this. We know the little trick we're going to use here, so we're going to just write this as 4 pi r squared at r plus delta r, r plus delta r. Right, so those are the, okay, let's put it together. So we could say here, we are interested in our overall material balance, which looks like this. So ddt delta Na, Na is this, and then the delta V is our choice, so it's a constant of differentiation, and the delta V we found to be this thing. And then Na we know is this. And Na at r plus delta r we know is this. And then the area here we know is this. And then, yeah, I forgot to do this one. 4 pi r squared. Okay, and we can see the 4 pi's can all cancel. And we can't cancel r squared because this r squared is evaluated at r plus delta r. But okay, let's get rid of the 4 pi's just quickly. And now we can take the same approach. We can say this is a trivial function in R. So that's R at R. And so we can write that there. And then we can see this function is evaluated at R plus delta R. So we can also say R squared there is the same as that. Okay, and then you can see here we want to divide by r squared, and this r squared can cancel with this r squared because it's at r, but this r squared is at r plus delta r, so we can't cancel that. So we have to take this out as a constant. So we'll do that here. can divide through by r squared. So we get rid of that. And then we divide through by the delta r. Divide by delta r. And oops. And of course, we can reverse the positions here. Actually, this minus sign came to the wrong place. So that actually belongs here. And then I'm going to reverse the position. So I'm going to move the second term up. So this is delta r. And then this one is a minus. That's the r there. So we've just switched those two terms around. Okay, and then you can see the expected form in this, right? It's going to be the same as what we saw for nabla squared. So it's DAE over r squared, and then you're going to have here DDR, so DDR of this function, right? That's after you take the limits. Right, so we can say, we should say here, taking the limits, delta r going to 0. Okay, so that's the exact same form as we saw in here, right? When we looked at our spherical coordinates, we saw the only term surviving was the r1, and it would have this form. So we can see that 1 over r squared and that r squared there, and then the second, well, the derivative of that stuff. Right, so you can see the same equation emerging there. The other thing we can do that we need to do is derive the boundary conditions here. And number one, we can say that the particles, let's say the particles entered with no sulfur dioxide in them, right? The whole point is we are trying to absorb sulfur dioxide into the particles. That means the particles are entering without sulfur dioxide. So let's just say that our particles, so at t equals 0, so they enter at t equals 0, and at all radial positions, there's none of the sulfur dioxide. So that's our initial condition. Then let's think about at the center of the particle. So if you think about this particle, right, at the center here, we expect that the gradients will be the same in all directions. Let's draw a new one. So if you were to draw a line through this, right? If you were to draw a concentration gradient here, right? I haven't drawn it well, but you can imagine it's quite symmetrical. So if you look at a cross section flat along the plane, it's like that. If you draw another cross section through it in this direction, you can also imagine at the center position, it's going to be a flat line. So all these flat lines mean near the center, because of symmetry, because you are exposed to the same concentration on all sides here, then it's all going to slope in the same way. And remember, when we draw these lines, we don't mean there's a specific plane or anything. You have to think kind of radially in all angles. So there's concentration is varying through the whole volume of it here, but it's varying in such a way that you've got the same stuff happening on all sides of the center position. And so we can easily imagine then that we have the symmetry condition there, so we can write dCA dr at position r equals 0. At position r equals 0. We can imagine that that's going to be a 0, right? So that's the symmetry condition. And then the last condition, you can think about the concentration out here. So again, the same story as we had before. Where was that with the slab? We did that in some detail. So here we had, this one? Yeah, this one. So with the slab, we had the high concentration inside the space of interest, and then it was diffusing out, and we wrote the equilibrium condition. In this case, the positions are reversed. In this case, the concentration is high in the air and it's low in the particle. So in this case, we have it would look more like this. It would look more like this. You'll get your discontinuous jump for the phase change, and then you get that, right? So this is the position R equals, and this is going to be the radius of the particle. So here we are talking about, if you look at the particle, let's draw it here like this. So if you think about the particle, R equals 0, we have a condition here, and then we are saying at the surface, you've got this SO2 out here trying to diffuse its way in. And so just outside here, there's the gas concentration. There's a discontinuous jump to the concentration inside the particle. And then there's diffusion inside here. Out here also, generally speaking, there's a variation in concentration until you reach the bulk value. So that's what we've drawn here. So there's the other condition. So at R equals 0, we can say, at R equals R naught, we can say that the concentration A for all time just inside the particle, so R equals R 0, and I'm going to use a superscript minus to denote just inside the particle. That's going to have an equilibrium. There's going to be the equilibrium shift with the concentration of A in the gas. And again, that might be, if the gas is well enough mixed, then for CAG, we can use the bulk value. If it's not well enough mixed, then we can say that's the concentration across that there's some difference, that here's your bulk value, and then there's a difference, and there's a value just outside the particle. Yeah, just be careful of these little things. Okay, and of course, you should read up on the film theory, so that's in your notes as well. So in the film theory, we have a nice, easy way to relate those concentrations. So the bulk concentration and the surface concentration, we use the simplification of the mass transfer coefficient. So just check out that lecture if you haven't already. So there are significant attempts to try to simplify this calculation. Okay, so that's it. Those are 3 boundary conditions, and you needed 3 boundary conditions in this case. Okay, any questions or comments there? Because that's pretty much it. Those are the 3 problems we wanted to cover today. So you can see the pattern here. If you've been keeping up with the developments, you should feel that you've got something like a superpower now. You've got this one equation which describes all the variables you've been exposed to on this course, right? You've seen in the first part of the course temperature and momentum. And if you look back at those equations, they had the same form as this, right? Remember, with momentum, you had a u ddx of u term, and then you had viscosity times d2u dx squared, right? So by analogy with momentum, this is your viscosity term, and then this was your convection term, right? So that's what you saw in terms of momentum. In terms of energy, you had the convection term. You had a ddx of temperature times u, and then times heat capacity or whatever. So you had some correction factor for that, but that form you had there. And then you also had the concept of conductivity. So you had here your conductivity times d. Sorry, 1 second. Sorry about that. So in the energy balance, where for alpha you were using T for temperature, you had the conductivity and you had d2t dx squared. So that was your conduction term, right? So you had conduction and convection. In momentum, you had viscosity and convection. In material balances, you have diffusion and convection. And like I mentioned in the video on this, for electrical fields, you also have you and I must confess I don't know that field well enough, right? I just noticed that it has the same form, but in electrical engineering, they have current flow, so their convection term. They have current flow, so it has the same form like this. So the electric field, so the gradient in the electric field multiplied by current, that's their version of convection. And then they also have a kind of electrical dissipation. So the decay of the electric field, they also have a term like that. So you see, this equation covers all of nature, really. This equation tells us that our view of the fluid has become kind of specific, that there's something more intrinsic behind the balances that we are developing. So it's telling us that molecules are actually they have two kind of components. There's a bulk movement of molecules, and then the molecules also have a dissipative effect. And so that's how we interpret this. When you find a situation where you've got many equations needed to describe one thing, right, the fluid, and they all have the same form, then that tells you that it might be in your original design, right? This choice of separating into mass and energy and momentum and electric fields, that there's actually something more intrinsic than that. So it might be, hopefully, that there'll be some new theory in the future where we have some kind of unifying thing. So a unifying concept. So it might simply be that this concept and this notion of a fluid is flawed, and that's why we end up with these multiple versions describing the same thing. But anyway, for now, we can at least say we have this nice, easy equation, and we can just modify it to our purpose and derive the balances that we need to describe the fluid in the way that we've been describing it. Okay, any questions or comments there? How many are we down to now? Okay. Okay, so if not, that's it for today. See you in the next one.